Hello, and welcome to Space for Sleep. For most of human history, the planets we knew were the ones we could see from home. Mercury, Venus, Mars, Jupiter, and Saturn moved against the background stars. Earth was eventually understood as one of them. Uranus and Neptune were added after telescopes and mathematics reached beyond naked eye astronomy. For a long time, that was the full planetary inventory of the universe as far as evidence was concerned. One star, our sun, and the worlds orbiting it. The idea that other stars might have planets was ancient. It was also unreachable. A planet beside another star is almost impossibly hard to see. The star is bright, the planet is faint. The star is far away, the planet is close to it in the sky. Even a giant planet like Jupiter, if placed around a nearby star, would be drowned in glare. An Earth-like world would be billions of times dimmer than the star it orbited. For centuries, the question was not whether imagination could picture other worlds, but whether measurement could ever prove them. Then measurement did prove them. The first confirmed exoplanets were found not around a calm sun-like star, but around a pulsar, the dense, rapidly spinning remnant of a dead star. A few years later, in 1995, astronomers confirmed 51 Pegasi b, the first planet discovered around a sun-like star. It was not what anyone expected, a giant planet orbiting extremely close to its star, completing a year in only a few days. The first normal star exoplanet was not a second Jupiter in a familiar outer orbit. It was a hot Jupiter, a world that forced astronomers to rethink planet formation almost immediately. Since then, the flood has not stopped. Kepler revealed thousands of planets by watching stars dim as planets crossed in front of them. TESS extended the search across nearly the whole sky. Ground-based spectrographs measured stellar wobbles with meter-per-second precision. Direct imaging instruments began photographing young giant planets in wide orbits. Microlensing surveys found cold worlds and free-floating candidates. The James Webb Space Telescope began reading molecular fingerprints in exoplanet atmospheres. By 2026, the confirmed catalog had passed 6,000 planets, with thousands more candidates still waiting for validation. The result is not a universe filled with copies of our solar system. It is stranger than that. There are hot Jupiters skimming their stars, lava worlds with molten day-sides, super-Earths and mini-Neptunes unlike anything around the Sun, compact systems packed inside Mercury-like orbits, circumbinary planets with two suns, planets around dead stars, rogue worlds with no star at all, and nearby rocky planets whose atmospheres may become the first places where we search seriously for signs of life. Exoplanets changed one of the oldest human questions. We no longer ask whether worlds exist around other stars. We ask what kinds of worlds they are, how common Earth-like planets may be, whether atmospheres survive around small red stars, whether biosignatures can be detected across light years, and whether life is a rare accident or a common planetary outcome. This is the story of worlds beyond our sun, not as fantasy, but as measured astronomy. It is worth pausing on how dramatic this shift was. Before exoplanets were detected, the solar system was not merely our local example. It was the only example. Every theory of planet formation had to be built from one system, and one system is a dangerous sample size. The solar system suggested a tidy architecture, small rocky planets inside, giant planets outside, nearly circular orbits, all planets moving in the same direction in roughly the same plane, and a large gap between terrestrial planets and ice giants. It was tempting to treat this as normal. The first discoveries broke that temptation. Hot Jupiters should not have been where they were. Pulsar planets should not have been easy to explain at all. Compact multi-planet systems did not resemble our widely spaced planetary arrangement. Super-Earths and mini-Neptunes, the most common planets Kepler found, were missing from our system entirely. Exoplanets did not simply add new objects to astronomy. They turned the solar system from a template into one case among many. This is why the exoplanet revolution is comparable, in its own way, to the Copernican shift. Copernicus moved Earth away from the center of the solar system. Exoplanet science moved the solar system away from the center of planetary imagination. Our system is important because it is home, and because it contains the only known biosphere. But it is not the default pattern. It is not the blueprint. The galaxy builds planetary systems with far more freedom than our local arrangement suggested. That realization matters for the search for life. If other systems were all simple variations of our own, we could search using familiar expectations. But exoplanets have taught us that familiarity is unreliable. Habitability may occur around red dwarfs, around orange dwarfs, on tidally locked planets, on ocean worlds, on moons of giant planets, or in subsurface environments no telescope can easily detect. A planet can be common without being Earth-like. A planet can be Earth-sized without being habitable. A planet can be in the habitable zone and still have no atmosphere. The catalog gives abundance, but it also demands caution. To understand why exoplanets are so diverse, it helps to return to the beginning of a planetary system. A star forms inside a cold molecular cloud, but not all the material falls directly into the star. Because the original cloud has some rotation, even if slight, the collapsing gas cannot simply fall straight inward. Conservation of angular momentum flattens part of the material into a rotating disk around the young star. This protoplanetary disk is the construction site of planets. Gas, dust, ice, metals, silicates, and organic molecules moving in a thin, turbulent, irradiated environment. The first solid building blocks are tiny dust grains. They collide, stick, grow, break apart, and stick again. Growth from micron-sized grains to kilometer-sized planetesimals is one of the difficult stages in planet formation because particles at intermediate sizes can drift inward rapidly due to drag from the gas disk and can also bounce or fragment instead of sticking. Several mechanisms may help, including streaming instabilities, where concentrations of pebbles become dense enough to collapse gravitationally into larger bodies. Once planetesimals form, gravity becomes more important. Larger bodies grow faster because they attract more material. Collisions build planetary embryos. In the inner disk, where temperatures are high, rock and metal dominate. Farther out, beyond the snow line, water ice and other volatiles can condense, increasing the amount of solid material available. This is why giant planet cores are expected to form more easily beyond the snow line. A core of several Earth masses can begin capturing gas from the disk before the disk disperses, eventually becoming a gas giant if conditions allow. But disks do not last forever. The gas is removed by accretion onto the star, by planet formation, by stellar radiation, and by winds. Most protoplanetary gas disks disappear within a few million years. That creates a deadline. A planet that fails to capture gas before the disk disperses will not become a Jupiter. A rocky planet can continue assembling through collisions after the gas is gone, but a gas giant depends on timing. This makes planetary systems sensitive to initial conditions. Disk mass, metallicity, turbulence, stellar radiation, nearby massive stars, the timing of core formation, and migration through the disk can all change the final architecture. A small difference early can produce a system with hot Jupiters, compact super-Earths, wide giants, resonant chains, or unstable scattering. The diversity of exoplanets is therefore not an accident added after formation. It is built into the physics of disks. Planet formation is not a factory producing one standard design. It is a competition between growth, migration, collisions, gas loss, radiation, and gravity. The first exoplanets were not found where scientists expected to find them, and they were not found using the method scientists had most anticipated would succeed. For decades, the expected first discovery was expected to come from direct imaging, pointing a powerful enough telescope at a nearby star and simply seeing the planet in the star's proximity, the way you might photograph a firefly next to a lighthouse. The challenge with direct imaging is enormous. A star is typically 1 billion to 10 billion times brighter than the planet orbiting it, and the angular separation between the two, at typical interstellar distances, is tiny. Resolving a Jupiter-like planet in the glare of a star 100 light-years away is comparable, in contrast ratio and angular resolution terms, to resolving a firefly hovering near a lighthouse viewed from across a continent. The method that actually succeeded first was radial velocity, also called Doppler spectroscopy. The principle is elegant. When a planet orbits a star, the star doesn't simply sit still. Both the star and the planet orbit their common center of mass. Because the planet is much less massive than the star's motion is very small, but it is not zero. As the star moves slightly toward and slightly away from Earth in its tiny orbit around the system's center of mass, the wavelengths of light it emits are shifted, compressed slightly toward shorter, bluer wavelengths when the star moves toward us, stretched slightly toward longer, redder wavelengths when the star moves away. By measuring this Doppler shift in the star's spectral lines with high-precision spectrographs, astronomers can detect the star's velocity variations and infer both the period and the minimum mass of the orbiting planet. Mayer and Q. Low detected 51 Pegasi b this way in 1995. The planet they found was deeply unexpected. A gas giant with roughly half the mass of Jupiter, orbiting its star at a distance of only about 5 million kilometers, roughly 1/8 the distance of Mercury from our Sun. At that distance, a planet completes one orbit in just 4 days, and the stellar surface heating keeps the planet's atmosphere at over 1,000 degrees Celsius. Nothing in the prevailing theoretical models had predicted that giant planets could exist in such close orbits. The standard formation theory held that giant planets could only form in the cold outer regions of a planetary system, beyond the frost line, where volatile ices could condense and provide the solid cores needed to gravitationally capture the large gas envelopes that define Jupiter-class planets. 51 Pegasi b was therefore not just the first confirmed exoplanet around a sun-like star. It was an immediate challenge to the theoretical framework that had been expected to guide the search. Something was wrong with, or at least incomplete about, the models. Giant planets apparently could end up in close orbits. The mechanism eventually proposed, and now broadly accepted, is planetary migration. Giant planets form in the outer system as theory predicts, but then gravitational interactions between the planet and the disk of gas and dust from which it formed can cause the planet to spiral inward, losing angular momentum to the disk as it goes, until it settles into a close orbit or, if the migration is not halted, spirals into the star entirely. This process, called Type II migration, is now understood to be a common feature of planetary system evolution, and the class of giant planets in close orbits, hot Jupiters, are its most visible product. In the years following 1995, the radial velocity method continued to produce discoveries, rapidly filling in a picture of exoplanet demographics that was strange by solar system standards. Hot Jupiters were found around roughly 1% of Sun-like stars surveyed, far more common than anyone had expected from a formation theory that predicted giant planets should form and stay in outer orbits. But they were still only 1%, meaning 99% of surveyed stars did not host a hot Jupiter in a detectable orbit. Other giant planets at greater distances were found as well, as the patience of the surveys extended to orbital periods of years and then decades, and as instrumentation improved. The radial velocity method has fundamental limitations. It naturally favors finding massive planets in short orbits, because a more massive planet produces a larger stellar wobble, and a shorter orbit produces more frequent and therefore more easily detected velocity variations. Planets at Earth's distance from their stars or beyond produce stellar velocity variations of only meters per second, comparable to the precision achieved by the best spectrographs, and detection requires years of monitoring to accumulate enough orbital data. The full census of planetary systems, including small rocky planets at habitable distances, required a different technique. Radial velocity and transits are the two workhorse methods, but they are not the whole toolkit. Astrometry looks for the same stellar wobble as radial velocity, but instead of measuring the star's motion toward and away from us through Doppler shifts, it measures the star's tiny side-to-side motion on the sky. This is extremely difficult because the angles involved are tiny, but it is powerful because it can reveal planets in wider orbits and can help determine a planet's true mass rather than only a minimum mass. The European Gaia mission, built primarily to map the positions and motions of stars in the Milky Way, has also opened a new path for discovering massive planets and brown dwarfs through their subtle gravitational effects on host stars. Microlensing uses a completely different principle. When a star passes in front of a more distant background star, its gravity bends and magnifies the background star's light. If the foreground star has a planet, the planet can create a brief additional distortion in the lensing signal. Microlensing is valuable because it can detect planets at wide orbital separations, planets around faint or distant stars, and even free-floating planets that are not bound to any star. Its weakness is that events usually do not repeat. A microlensing detection can reveal that a planet exists, but follow-up characterization is difficult because the alignment that produced the signal is temporary. Direct imaging is closest to the intuitive idea of seeing another world. It usually works best for young, massive planets far from their stars, because young giant planets still glow in infrared from the heat of formation, and wide orbits make them easier to separate from the glare of the host star. Direct imaging has produced some of the most visually striking exoplanet discoveries, including multi-planet systems where several giant planets can be seen orbiting the same young star. But it is not yet the main method for finding Earth-like planets, because an Earth twin around a Sun-like star would be faint, close to its star in angular separation, and extraordinarily difficult to isolate. Transit timing variations add another layer. In compact multi-planet systems, planets tug on one another. These tugs cause transits to occur slightly earlier or later than they would if each planet orbited alone. By measuring those timing shifts, astronomers can infer the masses of planets, detect non-transiting companions, and reconstruct the gravitational architecture of a system. Some of Kepler's most important multi-planet systems were characterized this way. Each method has biases. Radial velocity prefers massive close in planets. Transits prefer planets whose orbits happen to line up edge-on from Earth's point of view, and short-period planets produce more repeat transits. Direct imaging prefers young giant planets far from their stars. Microlensing is sensitive to distant and cold planets, but events are brief and hard to repeat. No single method gives the true planetary census. The picture emerges only when all methods are combined. That is why exoplanet science is partly a science of selection effects. The planets we find first are not necessarily the planets that are most common. They are the planets our instruments are most likely to reveal. Hot Jupiters seemed prominent at first because they were easy to detect, not because they dominate the galaxy. Kepler shifted the picture towards small close-in planets. Roman's microlensing survey is expected to shift the picture again by probing cold worlds farther from their stars, including the kinds of planets that transit surveys miss. The transit method became the dominant approach for large-scale exoplanet surveys, and it transformed the field. A transit light curve contains more information than a simple dip. The depth of the dip tells astronomers the planet's size relative to the star. The timing of repeated dips gives the orbital period. The shape of the transit, how quickly the brightness falls and rises, how long the planet remains fully in front of the star, whether the path crosses the center or the edge of the stellar disk, constrains the planet's orbital geometry. If the star's size is known, the planet's radius can be calculated. If the planet's mass is measured by radial velocity or transit timing variations, the density can be estimated, and density is the first clue to composition. A rocky planet has a different density from a gas-rich planet. A planet with an iron-rich core may be denser than Earth. A planet with a thick hydrogen envelope may have a large radius but low density. A water-rich planet may fall between rock and gas. These estimates are not always unique, because different internal structures can produce similar mass and radius combinations, but they narrow the possibilities. Transits also reveal atmospheres through several related techniques. Transmission spectroscopy studies starlight filtered through the atmosphere during transit. Emission spectroscopy compares the system before and during secondary eclipse, when the planet passes behind the star and its dayside light is temporarily removed from the total signal. Phase curves measure how the brightness of the planet-star system changes over the planet's orbit, revealing temperature differences between day and night, and sometimes even atmospheric circulation. For hot Jupiters, phase curves have shown winds moving heat from dayside to nightside. For ultra-hot Jupiters, they reveal atmospheres so hot that molecules break apart on the dayside and recombine on the night side. For smaller planets, these signals are much harder, but the principle is the same. A planet is not only detected by its shadow. It can also be studied by the light it absorbs, emits, reflects, and blocks. This is the transformation of modern exoplanet science. A point in a catalog becomes a physical world. First a period, then a radius, then a mass, then a density, then an atmosphere, perhaps, then clouds, temperature, chemistry, and eventually, one day, maybe surface conditions. When a planet's orbit is oriented such that it passes in front of its parent star as seen from Earth, a transit, it briefly blocks a small fraction of the star's light. A Jupiter-sized planet transiting a sun-like star blocks about 1% of the starlight. An Earth-sized planet transiting a sun-like star blocks about 1/100%, a tiny dip, but detectable by precise photometric instruments. The Kepler Space Telescope, launched in 2009, was specifically designed to exploit this method by staring at a single field of roughly 150,000 stars continuously for 4 years, measuring each star's brightness thousands of times to detect the periodic dips in brightness caused by transiting planets. Kepler operated from 2009 to 2018, with a change in mission profile in 2014 when 2 of its 4 reaction wheels failed, and it shifted to a different observing strategy, producing what became called the K2 mission. In its original and extended phases, Kepler found more than 2,600 confirmed exoplanets, providing the first large, statistically meaningful census of the galaxy's planetary population. What that census revealed was dramatic. The most common type of planet in the galaxy, at least at the orbital distances accessible to Kepler's 4-year baseline, is something that doesn't exist in our solar system: the super-Earth or mini-Neptune. These are planets with radii between roughly 1.5 and 3 times Earth's radius, and masses between a few and about 20 times Earth's mass, intermediate between the rocky terrestrial planets of the inner solar system and the ice giants Uranus and Neptune. They appear to be present around roughly 30 to 50% of Sun-like stars within the range of orbital periods accessible to Kepler, making them the most common category of planet detected. This was unexpected. Our solar system, with its clear gap between the rocky inner planets topping out at Earth's size and the gas giants starting at Uranus's size, had seemed perhaps typical. It is not. Statistically, our solar system's architecture, with no planet between Earth and Neptune, is unusual. Most planetary systems around other stars feature at least one planet in this intermediate size range, orbiting often at distances smaller than Mercury's distance from our Sun. Kepler's greatest contribution was not only the number of planets it found, it was statistics. A single planet can be spectacular and scientifically important, but it does not tell us how common planets are. Kepler was designed to answer the population question. By observing the same stars continuously, it could detect repeated transits and measure how frequently planets of different sizes and periods occurred. Because only a small fraction of planetary systems are aligned so that transits are visible from Earth, every detected transit planet implies many similar planets whose orbits are tilted away from our line of sight and therefore never transit. This geometric correction is crucial. If one Earth-sized planet is found transiting at an Earth-like distance around a Sun-like star, that does not mean only one such planet exists in the surveyed sample. It means one system happened to be aligned correctly. Many more could exist with the wrong geometry. Exoplanet occurrence rates are therefore statistical reconstructions, not simple counts. Kepler also revealed that compact multi-planet systems are common. Many stars host several planets orbiting closer than Mercury does to the Sun. These systems often have planets with sizes between Earth and Neptune, packed into nearly coplanar orbits. They are dynamically ordered, but unfamiliar. They raise questions about migration, atmospheric loss, and why our own inner solar system contains no super-Earth. The absence of a super-Earth in the solar system is now one of the interesting facts about home. It may reflect Jupiter's early migration, the distribution of material in the solar nebula, collisions during planet formation, or chance. Whatever the explanation, Kepler showed that a planetary architecture without a close and super-Earth is not the most common outcome. The physical nature of these super-Earth or mini-Neptune planets is one of the most active areas of current exoplanet research. There is a characteristic gap in the size distribution of small exoplanets, a dearth of planets with radii between about 1.5 and 2 times Earth's radius, known as the radius gap or Fulton gap, identified in 2017 by Benjamin Fulton and colleagues from precise Kepler data. Planets below this gap tend to be rocky, with densities consistent with rock and metal. Planets above the gap tend to be significantly less dense, suggesting they have retained substantial hydrogen-helium envelopes or large water-rich layers. The gap itself is thought to represent a transition driven by atmospheric photoevaporation, intense radiation from the host star stripping away the atmospheres of smaller planets, leaving behind bare rocky cores for those that started with too little gas to resist the stripping, while larger, more massive planets retain their envelopes. This evaporation creates the gap as a natural selection effect in the population of surviving planets. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018 as Kepler's successor, has continued the transit search with a different strategy. Rather than staring at a single field, TESS surveys the entire sky in segments, observing each sector for roughly a month before moving on, covering more stars in total but with a shorter baseline per star. This design makes TESS most sensitive to short-period planets around nearby, bright stars, nearby enough that detailed follow-up characterization is feasible, and it has discovered thousands of additional planet candidates, with confirmed planets continuing to accumulate. The nearby stars that TESS identifies as planet hosts are precisely the systems most amenable to detailed atmospheric characterization with the James Webb Space Telescope and future observatories. The James Webb Space Telescope, operational since 2022, represents the current frontier of exoplanet atmospheric characterization, the capability to study not just whether a planet exists, but what it's made of at its surface or in its atmosphere. When a transiting planet passes in front of its star, a small fraction of the star's light passes through the planet's atmosphere, if it has one, on its way to our telescopes. Different molecules in the atmosphere absorb specific wavelengths of light with characteristic fingerprints, producing absorption features at specific wavelengths in the stellar spectrum measured during transit. By comparing the spectrum measured during transit with the spectrum measured when the planet is not in front of the star, astronomers can identify the chemical composition of the planet's atmosphere, in principle detecting water vapor, carbon dioxide, methane, ammonia, ozone, and other molecules. This technique, transmission spectroscopy, is the primary tool of exoplanet atmospheric science. Hubble Space Telescope's instruments had already detected water vapor and other molecules in the atmospheres of several hot Jupiters and some smaller planets. But Webb's dramatically larger collecting area, its extended wavelength coverage reaching into the infrared where many important molecular features are strongest, and its improved sensitivity have pushed the technique to far greater precision and range. In one of its early demonstrations, Webb observed the hot giant JWST P96b and revealed water vapor, haze, and evidence of clouds in its spectrum with unprecedented clarity, a level of detail that showed how powerful Webb would be for exoplanet atmospheres. More scientifically significant for molecular chemistry was Webb's detection of carbon dioxide in the atmosphere of JWST P39b, a hot Saturn mass planet, providing the first unambiguous detection of carbon dioxide in an exoplanet atmosphere and demonstrating that Webb could access molecular features previously beyond reach. The targets that have attracted the greatest scientific attention are the TRAPPIST-1 planets, a system of 7 Earth-sized planets orbiting a small, cool red dwarf star approximately 40 light-years from Earth, announced in 2017 from observations by the TRAPPIST telescope in Chile and the Spitzer Space Telescope. At least 3 of these planets orbit within or near the habitable zone. The range of distances from the host star, where temperatures could in principle allow liquid water on a planet's surface, making the TRAPPIST-1 system the most concentrated set of potentially habitable worlds known. Webb has been observing the TRAPPIST-1 planets extensively. Early results have included the secondary eclipse measurement of TRAPPIST-1b, the innermost planet, too hot to be habitable, which suggested no substantial atmosphere, the planet's dayside temperature being close to what would be expected for a bare rocky surface with no greenhouse warming. Measurements of TRAPPIST-1c, slightly farther out, and still too warm for liquid water, but potentially with thin atmosphere, similarly suggested a thin or absent atmosphere. These results don't rule out atmospheres on the habitable zone planets farther out, TRAPPIST-1d, E, F, and G, but they show that at least the innermost planets in this system may have lost their atmospheres under the intense radiation environment of their small, active red dwarf host. The full characterization of the TRAPPIST-1 system's atmospheric properties will require continued Webb observations over many years and represents one of the most eagerly anticipated ongoing investigations in all of astronomy. Some individual planets have become laboratories for entire categories of physics. JWST P39b, for example, is a hot Saturn-like planet whose atmosphere has been studied in detail by Webb. It is not habitable, and it is not trying to be Earth-like. Its scientific value is different. It is large, hot, puffy, and accessible to spectroscopy. In its atmosphere, Webb has detected molecules and signatures that help astronomers understand atmospheric chemistry under intense stellar irradiation, including carbon dioxide and sulfur dioxide produced through photochemistry. A planet like this is not interesting because it resembles home. It is interesting because it lets scientists test how atmospheres behave under conditions the solar system does not provide. TRAPPIST-1 is important for the opposite reason. It is small, nearby, and compact, with 7 roughly Earth-sized planets around an ultra-cool red dwarf. The planets are not separated by vast distances like the planets in our solar system. They are packed close together, many in resonant relationships, tugging one another enough that their transit times reveal their masses. The system is a natural laboratory for rocky planets around the most common type of star in the galaxy. But TRAPPIST-1 also teaches caution. Earth size does not mean Earth-like. Several of the planets receive too much radiation for surface habitability. The star is active. Atmospheres may be stripped or altered. Early Webb measurements of the innermost planets have not revealed thick atmospheres, though the more temperate outer planets remain harder to characterize. The system is still one of the best targets for studying small planets, but it has not answered the life question. LHS 1140b is another important nearby target, a temperate planet around a red dwarf that may be rocky or volatile-rich, depending on its exact properties. It is interesting because it is relatively favorable for atmospheric study compared with many other small habitable zone candidates. Proxima Centauri b is compelling because it orbits the nearest star to the Sun, but its non-transiting geometry and active stellar environment make it difficult. TOI 700d and related planets show that TESS can find small planets in habitable zone orbits around nearby red dwarfs, giving future telescopes a better target list. These worlds do not form a simple ranking from worst to best. They form a portfolio. Some are best for atmospheric chemistry. Some are best for formation theory. Some are best for habitability modeling. Some are best for testing stellar activity. Some are valuable because they are nearby, others because they are extreme. Exoplanet science advances by comparing all of them. The practical challenge of observing exoplanets is almost absurd in scale. A star does not politely dim itself so that its planets can be seen. The planet's signal is usually buried under stellar brightness, stellar activity, instrumental noise, detector behavior, cosmic rays, background stars, and the movement of the telescope itself. A transit may reduce a star's light by only a few hundred parts per million. An atmospheric feature may be a few parts per million within that already tiny signal. To find it, astronomers must understand the star, the instrument, and the statistics with extraordinary care. This is why confirmation matters. A candidate planet is not yet a planet. Eclipsing binary stars, star spots, instrumental systematics, background blends, and random noise can mimic planetary signals. Confirmation may require radial velocity follow-up, additional transits, high-resolution imaging to rule out nearby contaminating stars, statistical validation, or combinations of methods. Some candidates disappear under closer analysis. Others survive and become confirmed worlds. Even confirmed planets can change as measurements improve. A radius estimate may be revised when the host star's size is better known. A mass may shift with new radial velocity data. An atmosphere once thought likely may disappear when Webb or another telescope observes a flat spectrum. The catalog is alive because the data are alive. Scientific knowledge here is not a fixed list, but a process of continual refinement. This is especially important for public communication. Exoplanet headlines often move faster than the evidence. A planet becomes Earth-like because it has a similar radius. A molecule becomes a possible sign of life because on Earth biology produces it. A habitable zone orbit becomes a habitable world, but each step adds assumptions. A careful script has to keep the wonder without overstating the certainty. The truth is already astonishing. It does not need exaggeration. Atmospheric characterization is where exoplanet science becomes both most exciting and most dangerous for interpretation. A spectrum is not a photograph of an atmosphere. It is a pattern of light filtered through a complicated system. The star, the planet, the instrument, the data reduction pipeline, clouds, hazes, temperature structure, molecular opacities, and the assumptions built into atmospheric retrieval models. A molecule may leave a feature at a certain wavelength, but other molecules can sometimes produce similar features. Clouds can flatten a spectrum. Stellar activity can contaminate a signal. The same dataset can sometimes support several atmospheric models unless the signal is strong and the wavelength coverage is broad. This is why claims about biosignatures require exceptional caution. The case of K218b is a useful example. Webb observations have provided evidence for molecules such as methane and carbon dioxide in the atmosphere of this temperate sub-Neptune, and some analyses have discussed possible sulfur-bearing molecules such as dimethyl sulfide or dimethyl disulfide. On Earth, dimethyl sulfide is associated with biological activity, especially marine microorganisms. But that does not make a tentative spectral hint a detection of life. The signal has been debated. Independent analyses have questioned its robustness, and the planet itself is not an Earth twin. It is larger than Earth, likely has a hydrogen-rich atmosphere, and may have conditions very different from an ocean planet with a breathable sky. The responsible scientific position is clear. K218b is fascinating, but it is not evidence that life has been found. It is a case study in how difficult biosignature science will be. A real detection of life beyond Earth would require not one molecule in isolation, but a robust atmospheric context, repeated observations, careful elimination of false positives, and broad scientific agreement that non-biological explanations are unlikely. This caution does not weaken the search. It strengthens it. Exoplanet science is entering a period where biology may become an observational question, and that means the standards must be high enough to survive the importance of the claim. Let's step back from the methods and current missions and talk about the strange diversity of what has actually been found, because the population of known exoplanets contains individual systems and objects that challenge intuition at every turn. Hot Jupiters are perhaps the most studied category of exoplanet, partly because they were the first to be discovered and partly because their large size and short orbital periods make them observationally convenient. Their properties have turned out to be dramatically different from Jupiter in many ways. The tidally locked nature of most hot Jupiters, with one hemisphere permanently facing the star and the other permanently in darkness, the planet rotating once per orbit, produces extreme atmospheric dynamics, with superrotating equatorial jet streams that move heat from the hot day side to the cooler night side. Some hot Jupiters have been found to have distinctly inflated radii, significantly larger than models would predict for their mass, given the radiation they receive, and the mechanism for this radius inflation remains a matter of ongoing debate, with proposed mechanisms including tidal heating, ohmic dissipation of magnetic currents in the atmosphere, and kinetic heating from atmospheric circulation. Some hot Jupiters have been found to have highly reflective, cloud-laden atmospheres, while others appear strikingly dark, absorbing nearly all incoming stellar radiation. Kepler 7b, for instance, has one of the highest albedos measured for any exoplanet, reflecting about a third of incident starlight, while JWST absorbs almost all of it, with an albedo close to zero, darker than coal, possibly because at its extreme temperature of around 2,500 Kelvin, molecules are thermally dissociated and the resulting atomic iron and other metals absorb visible light efficiently in a cloud-free, molecular poor atmosphere. JWST is remarkable in multiple ways. It is so close to its host star, orbiting in just over a day at a distance of roughly 3 million kilometers, that tidal forces from the star are literally pulling the planet apart. Material is flowing off the planet's upper atmosphere, forming a cloud around the planet and being accreted onto the star. JWST is in the process of being consumed by its star, with an estimated remaining lifetime of a few million years before it spirals into the stellar surface completely. Observing it now is observing a planet in its final stages, a giant world being actively eaten, losing mass at every orbit, tightening its spiral inward with each pass. Ultra-hot Jupiters represent the most extreme end of the hot Jupiter population, with dayside temperatures exceeding 2000 Kelvin and in some cases approaching or exceeding 4000 Kelvin, hotter than many stars. These planets have atmospheres where molecular hydrogen is thermally dissociated into atomic hydrogen on the day side, and metals like iron, titanium, and vanadium are found in gaseous form. KELT-9b, the hottest known exoplanet, orbits a star hotter than our Sun in just 36 hours and has a dayside temperature of roughly 4,300 Kelvin, hotter than many red dwarf stars. Its atmosphere contains atomic iron, titanium, magnesium, and scandium in detectable quantities. The night side is far cooler, but the dramatic temperature difference between day and night drives winds circulating at thousands of kilometers per hour, and the atmosphere above the terminator, the boundary between day and night, is in a perpetual state of molecular dissociation and recombination as gas flows from the scorching day side to the cooler night side and back. Many of the most common exoplanets force astronomers to use words that are still provisional. A super-Earth is not necessarily Earth-like. It means larger than Earth and smaller than Neptune, usually by mass or radius, depending on the measurement available. Some super-Earths may be rocky worlds with deep mantles and intense gravity. Others may have volatile rich envelopes, thick atmospheres, or high-pressure water layers. A mini-Neptune is not necessarily a small Neptune. It may be a rocky core wrapped in a hydrogen-helium atmosphere, or a water-rich planet with a steam atmosphere, or a transitional object shaped by atmospheric escape. The radius gap is one of the strongest clues that these planets evolve. Close to a star, high-energy radiation can strip the atmospheres from smaller planets, leaving bare rocky cores below the gap. Larger planets hold on to gas and remain above it. Another process, core-powered mass loss, may also contribute. Heat left over from formation escapes from the planet's interior and drives atmospheric loss from the inside out. The final population we observe is therefore not only a record of formation, it is a record of erosion. Lava worlds form the extreme rocky end of this population. These are planets so close to their stars that their day sides may be molten, with rock vapor atmospheres and night sides cold enough for minerals to condense. On such worlds, weather may involve silicate vapor, metal clouds, or molten rock rain rather than water. The boundary between geology and atmosphere becomes blurred. Water worlds are another possibility. A planet that forms beyond the snow line and migrates inward may carry a large fraction of its mass as water, but deep global oceans are not automatically friendly to life. Under enough pressure, water can form high-pressure ice phases at the ocean floor, separating liquid water from rocky material below and perhaps limiting the geochemical cycles that help regulate habitability on Earth. A planet can have more water than Earth and be less Earth-like because of it. This is one of the central lessons of exoplanets. Size is not destiny. Radius, mass, density, orbit, host star, atmosphere, age, and formation history all matter. A planet can sit in the habitable zone and be sterile. A planet can be Earth-sized and airless. A planet can be larger than Earth and still have a rocky surface, or it can be wrapped in gas so deep that no surface exists in the ordinary sense. The name of a category is only the beginning of the question. Let's turn to some of the most physically strange and conceptually challenging individual systems found in the exoplanet census. PSR 1257+12 was the site of the first confirmed exoplanet detection of any kind, predating the 51 Pegasi b discovery by 3 years. It is a pulsar, a rapidly rotating neutron star, and the planets found orbiting it were discovered not through stellar wobbles or transits, but through timing variations in the pulsar's extraordinarily regular radio pulses. As planets orbit the pulsar's distance from Earth changes slightly, causing the arrival times of its pulses to vary in a characteristic pattern. The discovery, by Alexander Woolston and Dale Frail in 1992, was initially received with skepticism. Planets around a pulsar seemed deeply implausible, given that pulsars form in supernova explosions that would destroy any pre-existing planetary system. The eventual consensus is that the PSR 1257+12 planets formed from the disk of debris left by the supernova, assembled from the wreckage of a previous planetary system after the star's catastrophic death. These are second-generation planets, worlds formed from the remnants of destruction, orbiting the corpse of a star that once shone and then violently died. Whatever environmental conditions exist on these worlds, they are bathed in intense pulsar radiation, not sunlight. HW Virginis hosts a close binary star system, 2 stars orbiting each other in less than 3 hours, and appears to have at least one large planet orbiting both stars together, a circumbinary planet. Circumbinary planets, sometimes called Tatooine worlds after the fictional double sun planet from the Star Wars films, are real and have been found in multiple systems. The most famous confirmed circumbinary planets come from Kepler data. Kepler 16b, announced in 2011, is a Saturn mass planet orbiting 2 stars with a combined mass slightly less than our Sun, producing the distinctive visual effect of the planet's shadow crossing both stellar disks sequentially in a complex pattern. The existence of circumbinary planets around tight binary systems constrains their formation, since the gravitational perturbations from 2 orbiting stars create a dynamically unstable environment in the inner parts of the circumstellar disk, requiring planets either to form farther out and migrate inward, or to form through a mechanism less dependent on stable, long-lasting disk conditions than conventional core accretion scenarios assume. Kepler 16b and its counterparts orbit outside the so-called instability zone around binary stars, where gravitational perturbations would eventually eject any planet. But for a hypothetical observer on the surface of such a circumbinary world, the sky would be dramatically different from our own. 2 suns, of different sizes and colors, would move through the sky in complex patterns relative to each other and relative to the planet. Days would not have a single sunrise and sunset, but a variable sequence of one or both stars rising, setting, or being eclipsed by each other, producing lighting conditions with no analog in any single star system. Depending on the binary's period and the planet's orbital period, there would be times of double sunset, both stars simultaneously near or at the horizon, and times of intense double daylight, as well as times when one star has set and only the dimmer or brighter companion remains visible. Kepler 11 was one of the most extraordinary multi-planet systems found by Kepler. It hosts 6 confirmed planets, all orbiting closer to their host star than Venus orbits our Sun, all transiting the star, and all with orbital periods between 10 and 118 days. The inner 5 planets are packed into orbital resonances. Their orbital periods are in simple integer ratios, the gravitational signature of a system that has been dynamically sculpted by planet-planet interactions and perhaps by migration through the early disk. None of the 6 planets has a density consistent with pure rock. They must have retained substantial volatile envelopes, and their individual densities range from water-like to foam-like. Kepler-11 is a demonstration that planetary systems can be far more compact, far more populated at short orbital periods, and far more dominated by sub-Neptune worlds than anything in our own system. The Kepler-90 system became especially famous in 2017 when machine learning applied to Kepler data revealed an eighth planet, Kepler-90I, that brought the system to 8 confirmed planets, matching our solar system's count. Though all 8 Kepler-90 planets fit within roughly Earth's orbital distance from the Sun, packed into a far more compact architecture than our own. Planetary systems are architectures, not just lists of planets. The spacing of orbits, the masses of planets, the presence or absence of giant planets, the tilt of orbital planes, and the eccentricity of orbits all preserve information about formation history. A system with several planets in near-resonant orbits may have migrated gently through a gas disk. A system with a hot Jupiter and no nearby small planets may have experienced violent migration or tidal evolution that cleared out the inner system. A system with a cold Jupiter far from the star may have protected or disturbed inner rocky planets, depending on its orbit. Our solar system has a particular architecture: small inner rocky planets, an asteroid belt, gas giants, ice giants, and outer small body reservoirs. But exoplanet systems show many other arrangements. Some have giant planets closer than Mercury. Some have chains of small planets in resonance. Some have planets on eccentric orbits that bring them through extreme temperature swings. Some have misaligned orbits, suggesting past gravitational scattering or interactions with companion stars. Migration is now understood as normal, not exceptional. Planets form inside disks, and disks are not passive. A planet raises waves in the gas disk. Those waves exchange angular momentum with the planet. Depending on the mass of the planet and the disk conditions, the planet can move inward or outward. Giant planets can open gaps in disks and migrate with the disk's viscous evolution. Smaller planets can migrate rapidly if nothing stops them. Resonant chains can form when multiple planets migrate together and lock into orbital ratios. Later, after the gas disk disperses, systems can become unstable. Planets can scatter one another, collide, fall into the star, or be ejected into interstellar space. The quiet architecture we observe billions of years later may be the survivor of a violent youth. TOI 700d was one of the first Earth-sized planets discovered by TESS in the habitable zone of its host star, a small, cool red dwarf about 100 light-years away. The planet is tidally locked, with one hemisphere permanently facing its star and the other in eternal night. But climate models suggest that under various atmospheric scenarios, liquid water might still be possible in the terminator region between the two hemispheres. TOI 700d has become a priority target for atmospheric characterization. Rocky planets in the habitable zones of their host stars are among the most eagerly sought-after targets in exoplanet science. But the concept of the habitable zone itself requires careful unpacking, because the popular shorthand, the region where liquid water can exist on the surface, conceals important complexity and uncertainty. The habitable zone is calculated based on the amount of stellar radiation a planet receives and a set of assumptions about the planet's atmosphere. The classic formulation, developed by James Casting and colleagues in the 1990s, defines the optimistic habitable zone as the range of distances within which a planet with a carbon dioxide water-nitrogen atmosphere could maintain surface temperatures above freezing for at least some portion of its orbit. The inner edge is determined by a runaway greenhouse threshold. Too much radiation and the water evaporates faster than it can be stabilized, amplifying warming uncontrollably, as happened on Venus. The outer edge is determined by a maximum greenhouse scenario. Carbon dioxide can continue providing greenhouse warming only to a certain concentration, beyond which further carbon dioxide addition causes the gas to reflect starlight rather than trap heat. These boundaries are themselves model-dependent, varying with assumptions about cloud behavior, surface pressure, and other parameters. The habitable zone is better understood as a probability gradient rather than a sharp boundary. Planets at the inner edge are more likely to be too hot, planets at the outer edge too cold, but individual planet properties, including atmospheric composition, surface geology, internal heating, and the presence of ocean or ice cover can push the actual conditions in either direction. The habitable zone also shifts with stellar type. Red dwarf stars, the most common stars in the galaxy, are much cooler and less luminous than our Sun, so their habitable zones are much closer in, at orbital distances comparable to or smaller than Mercury's distance from our Sun. This proximity creates a significant complication, tidal locking. Planets close enough to a red dwarf to receive sufficient warmth for liquid water are also close enough that tidal forces from the star lock the planet's rotation to its orbital period, keeping one hemisphere permanently illuminated and the other in permanent darkness. Early concerns that tidally locked planets might be climatically unsuitable for life, with the atmosphere freezing out on the dark side or heat circulation being insufficient to maintain habitable conditions, have been partially addressed by improved three-dimensional climate models, which generally suggest that tidally locked planets with reasonable atmospheric masses can maintain habitable temperature distributions across significant portions of their surfaces, with the strongest stellar radiation on the permanent day side, the cooler night side, and potentially habitable conditions in the terminator zone. Red dwarf habitable zones also present an activity hazard. Red dwarf stars, despite their small size and cool temperatures, can be extraordinarily magnetically active, producing flares far more intense relative to their quiescent luminosity than the flares our Sun produces. The TRAPPIST-1 system's host star, for instance, produces frequent intense UV and X-ray flares. The effect of this flare activity on the atmospheres of habitable zone planets is an active area of research. Some modeling suggests that ozone chemistry in nitrogen-oxygen atmospheres could protect surfaces from UV damage, while other models suggest that the combination of intense flare radiation and powerful stellar winds could erode atmospheres over geological timescales, particularly if the planets lack magnetic fields to deflect the stellar wind. The question of whether red dwarf habitable zone planets can maintain their atmospheres long enough for life to develop and survive is genuinely unresolved. Habitability also depends on time. Exoplanet climates may be far stranger than the climate categories familiar from Earth. On a tidally locked planet, the star never rises or sets. One hemisphere receives permanent daylight. The opposite hemisphere remains in permanent night. Early assumptions imagined such planets as divided into a boiling day side and a frozen night side, with atmosphere collapsing as ice on the dark hemisphere. But climate models have shown that a sufficiently thick atmosphere can move heat efficiently, carrying warmth from day to night through winds. Oceans, if present, can also redistribute heat. Clouds on the day side may reflect starlight and stabilize temperature. The most habitable region might not be the substellar point directly under the star, but a ring or broad region between day and night. On planets with eccentric orbits, seasons can be driven not only by axial tilt, but by changing distance from the star. A planet might spend part of its year frozen and part of its year thawing. If it has oceans or a thick atmosphere, thermal inertia could smooth those extremes. If it is dry and airless, the extremes could be brutal. A planet's climate is therefore not determined by average energy alone. Timing matters. Heat storage matters. Atmospheric circulation matters. Some planets may be covered by global oceans hundreds of kilometers deep. Others may be desert worlds with limited surface water, which in some models can remain habitable closer to the inner edge of the habitable zone because less water vapor enters the atmosphere to drive greenhouse feedback. A drier planet is not automatically less habitable. It may be more resistant to runaway greenhouse conditions. A water-rich planet is not automatically more habitable. Too much water can suppress the rock-water carbon cycles that help stabilize climate. Clouds are one of the great uncertainties. On Earth, clouds can cool by reflecting sunlight or warm by trapping infrared radiation, depending on altitude, thickness, particle size, and location. On exoplanets, clouds may be water, silicates, salts, hydrocarbons, or metals depending on temperature. They can hide molecular features in spectra, making an atmosphere look flat and featureless. They can also control climate enough to decide whether a planet is temperate or not. This means habitability is a systems problem. It is not enough to ask whether a planet receives Earth-like sunlight. We must ask what kind of star provides that light, whether the planet rotates, whether it has an atmosphere, how thick that atmosphere is, what gases it contains, whether clouds form, whether oceans exist, whether the surface cycles carbon, and whether the star's radiation removes the atmosphere over time. The simple phrase habitable zone is useful, but it is only a first filter. The real question is not whether a planet sits at the right distance. The real question is whether a planet has kept the right conditions through deep time. A planet may pass through habitable conditions only briefly. A young planet may be too hot after formation, then temperate for a while, then frozen or desiccated later. A star's luminosity changes. A planet's atmosphere changes. Volcanism can replenish gases. Impacts can remove them. Stellar radiation can erode them. Plate tectonics, if present, can regulate carbon dioxide over long time scales. The habitable zone is therefore not a static ring. It is a moving and model-dependent region around an evolving star. For red dwarfs, the time problem is especially important. These stars are long-lived, but their early phases can be extremely luminous and active relative to their later stable state. A planet now sitting in the habitable zone may have spent its first hundreds of millions of years receiving enough radiation to lose water, especially if it orbited close to the star. Whether such planets can retain or rebuild atmospheres is one of the most important questions in astrobiology, because red dwarfs are the most common stars in the galaxy. For sun-like stars, the challenge is different. Their habitable zones are farther out, reducing tidal locking concerns, but transits are rarer and atmospheric characterization is much harder. An Earth-sized planet crossing a sun-like star blocks only a tiny fraction of the starlight, and an Earth-like atmosphere leaves an even tinier spectral imprint. The planets most similar to Earth are not necessarily the easiest planets to study. This creates a strategic tension. The best near-term atmospheric targets are often planets around small red dwarfs, because the planet-to-star size ratio is favorable and transits are deeper. The most Earth-like targets may orbit larger, quieter stars, but require future direct imaging missions beyond current capabilities. The search for life will therefore probably proceed in stages, first testing nearby red dwarf systems, then moving toward true Earth analogs around Sun-like stars with future observatories. The search for biosignatures, chemical or physical markers in a planet's atmosphere that would indicate the presence of life, is the ultimate goal of exoplanet atmospheric science, and it is an area where the science is advancing rapidly, while the interpretation of potential signals remains deeply complex. False positives are one of the hardest problems in biosignature science. On Earth, oxygen is strongly associated with life because photosynthesis continually replenishes it. But on another planet, oxygen could accumulate without biology under certain circumstances. If water vapor reaches high altitudes and ultraviolet light splits it into hydrogen and oxygen, the lighter hydrogen can escape to space while oxygen remains behind. A planet that lost an ocean could develop an oxygen-rich atmosphere that is not biological at all. Conversely, a living planet might not show abundant oxygen if its biology is microbial, if oxygen is consumed rapidly by surface chemistry, or if its biosphere uses different metabolic pathways. Methane is also ambiguous. On Earth, it has biological sources, but it can also be produced by geological processes such as serpentinization, where water reacts with certain rocks. Nitrous oxide is promising but difficult to detect. Ozone can indicate oxygen, but can also be affected by photochemistry. Dimethyl sulfide is associated with life on Earth, but interpreting it on a hydrogen-rich sub-Neptune would require understanding atmospheric chemistry far beyond a simple Earth analogy. The strongest biosignatures may therefore be combinations. Gases that should not coexist for long unless they are being replenished, or atmospheric states that are difficult to maintain without biological fluxes. But even then, context is everything. The star's ultraviolet spectrum matters. The planet's mass matters. Surface pressure matters. Clouds matter. Geological outgassing matters. Ocean chemistry matters. A biosignature is not a molecule. It is an argument about a planetary system. There is also the problem of detectability. A biosphere could exist and be invisible to us. Life in an ocean beneath ice would not necessarily change the atmosphere. A microbial biosphere might produce gases too weak to detect across light years. A planet could have life, but no technological civilization, no radio leakage, no city lights, no obvious atmospheric imbalance at our current sensitivity. The absence of detected biosignatures will not mean the absence of life. It will mean only that our instruments have not found the kinds of life that produce detectable planetary scale signatures. This makes the search humbling. The first inhabited world we discover may not be obvious. The first true biosignature may be debated for years. And some living worlds may remain hidden not because they are rare, but because they are quiet. Oxygen is often discussed as the canonical biosignature. Our own atmosphere contains about 21% molecular oxygen, a reactive gas that would quickly be removed through oxidation of surface rocks if it were not continuously replenished by biological photosynthesis. The intuition is straightforward. Detecting substantial oxygen in an exoplanet atmosphere would suggest biological production. But this intuition has been substantially complicated by theoretical work showing that oxygen can accumulate to significant levels through purely abiotic processes, particularly in certain atmospheric scenarios around red dwarf stars, where photolysis of water vapor produces oxygen that doesn't easily recombine due to specific atmospheric chemistry. An oxygen detection alone, without additional context, would not be sufficient evidence for life. The concept of biosignature gases has been broadened to include combinations of gases that would be thermodynamically out of equilibrium with each other in the absence of ongoing biological production. For example, the simultaneous presence of methane and oxygen in significant quantities. Since the two gases react with each other and would not coexist in detectable amounts without continuous replenishment from biological sources. Other proposed biosignatures include nitrous oxide, dimethyl sulfide, a gas produced by marine phytoplankton on Earth, and the general vegetation red edge, a sharp increase in reflectivity at wavelengths just beyond visible red light produced by chlorophyll in plant leaves and potentially detectable in a planet's reflection spectrum. Detecting any of these signatures in an exoplanet atmosphere is far beyond current capability for most systems. Webb can probe the atmospheres of certain nearby super-Earths and sub-Neptunes with some sensitivity, but Earth twin planets around Sun-like stars remain entirely out of reach of current instrumentation. The required photometric and spectroscopic precision to detect an Earth-like atmospheric fingerprint through transit observations of a true Earth analog exceeds what any existing or near-term telescope can achieve. The next generation of ground-based extremely large telescopes, including the Extremely Large Telescope under construction in Chile, with a primary mirror 39 meters in diameter, and space telescope concepts, including the proposed Habitable Worlds Observatory designed specifically for direct imaging and spectroscopy of Earth-like planets around nearby sun-like stars, are the tools being built and designed to push this frontier forward in the coming decades. The rogue planets, planets that orbit no star, drifting freely through interstellar space without a host, represent a genuinely strange category of world that challenges the usual definition of what a planet is. Rogue planets are expected to be relatively common as a consequence of planet formation and dynamical evolution in young planetary systems. In the chaotic early stages of a planetary system's history, gravitational interactions between planets can eject some members of the system on hyperbolic trajectories, sending them outward at speeds exceeding the local escape velocity and launching them into interstellar space. Simulations of planetary system formation suggest that for every planet that survives in a stable orbit, roughly 1 or 2 may be ejected over the system's history. Extrapolating this to the billions of stars in the Milky Way suggests an enormous population of rogue planets drifting through the interstellar medium, potentially outnumbering the stars themselves. Detecting rogue planets is challenging precisely because they are dark, producing no light of their own and receiving no significant light from any nearby star. The primary detection method is gravitational microlensing, the amplification of light from a more distant background star when a massive object passes between the background star and Earth, bending the background star's light around it, and producing a characteristic brightening event that lasts days to months depending on the lensing object's mass. Several candidate rogue planets have been detected this way, including some that appear to be roughly Earth mass, smaller than gas giants, and potentially rocky, drifting through the galaxy without any stellar warmth. The largest and most directly observable rogue planets are the gas giant mass objects detected in star-forming regions, too young to have had time to cool significantly and therefore still glowing faintly in the infrared from their residual formation heat. These objects, sometimes called free-floating planetary mass objects or PLANEMOs, exist in a definitional ambiguity. If they formed from the collapse of a small gas cloud, as stars do, they might be better classified as substellar brown dwarfs. If they were ejected from forming planetary systems, they are rogue planets. The distinction is observationally difficult to make for any individual object and may not even be physically meaningful in every case. The recently identified rogue planet candidate CFHTWI OFF 98b, detected in the Ophiuchus star-forming region, appears to be a roughly 3 Jupiter mass object with a smaller companion roughly 1 Jupiter mass, potentially a rogue planet binary, a pair of planet mass objects gravitationally bound to each other but not to any star, drifting through a stellar nursery. This kind of object has no analog in our solar system and challenges the already blurred boundary between planets and brown dwarfs. The most widely discussed recent free-floating planetary mass objects found with Webb are the Jupiter Mass Binary Objects, or JUMBOs, reported in the Orion Nebula. These are candidate pairs of Jupiter mass objects that appear to be bound to each other while not orbiting a star. Their nature is still debated, and they should be described cautiously. They may be part of a broader population of very low-mass objects formed more like stars, or they may reflect dynamical processes that eject planet mass bodies while leaving some pairs intact. Either way, they are important because they blur the boundary between planets, brown dwarfs, and the lowest mass products of star formation. The lesson is not that every strange infrared point is automatically a planet. The lesson is that nature produces objects in the planetary mass range in more than one way, and classification is still catching up. A rogue planet with no star may sound lifeless by definition, but even here the possibilities are not simple. Without sunlight, the surface of a free-floating rocky planet would be extremely cold unless it retained a thick, insulating atmosphere. But internal heat remains. Radioactive decay, residual formation heat, and tidal heating if the rogue planet has a large moon could maintain subsurface oceans in some cases. A thick hydrogen atmosphere could, in principle, trap enough heat for liquid water at the surface even far from any star, though such worlds would be difficult to detect and even harder to characterize. Most rogue planets are probably dark and cold, but their existence matters because they reveal how violent planetary system formation can be. Every ejected world is evidence that forming systems are not always gentle disks settling into orderly orbits. They are gravitational arenas where planets scatter, collide, migrate, and sometimes lose their stars entirely. They also complicate the emotional meaning of the word planet. In the solar system, a planet is something that belongs to a star. But the galaxy may contain enormous numbers of planetary mass worlds moving alone through interstellar space. Some may have formed around stars and been expelled. Others may have formed directly from collapsing gas, like tiny failed stars. The boundary between planet and substellar object becomes less about appearance and more about origin, and origin is often the hardest thing to know. The diversity of stellar hosts for exoplanets is itself a source of important scientific information. Planets have been found around stars very different from our Sun, hotter and more massive A and F-type stars, cooler and smaller K and M dwarfs, metal-poor stars similar to the earliest generations of stars in the galaxy, and binary and multiple star systems of various configurations. The host star is not just a light source. It is the central environmental condition. A planet around an F-type star receives a different spectrum and evolves under a different stellar lifetime than a planet around a K dwarf or an M dwarf. Hotter stars emit more ultraviolet radiation and live shorter lives. Cooler stars live much longer but can be magnetically active, especially when young. A Sun-like star offers a balance familiar from Earth, but Sun-like stars are not the majority. K-dwarfs, slightly cooler and longer-lived than the Sun, are sometimes described as especially promising for habitability because they may offer long, stable lifetimes without the extreme flare behavior common among many red dwarfs. Metallicity shapes planets before they exist. A star rich in heavy elements likely formed from a disk rich in solid material. That makes it easier to build giant planet cores before the gas disk disappears. This is why gas giants are more common around metal-rich stars. Small rocky planets appear less strongly dependent on metallicity, but they still require heavy elements. In the earliest universe, before many generations of stars had produced carbon, oxygen, silicon, magnesium, and iron, planet formation would have been different and probably less efficient for rocky worlds. Binary stars add another layer. Some planets orbit one star in a binary, with the companion star far enough away to perturb the system but not destroy it. Others orbit both stars, circumbinary planets moving around a shifting double center. Planet formation in such systems is more complex because the gravitational field of two stars can stir the disk, truncate it, or create unstable zones. The existence of circumbinary planets shows that disks can still produce planets in environments that once seemed too chaotic. A planet is therefore never separate from its star. The same planet placed around a different star would have a different climate, atmospheric escape history, radiation environment, year length, tidal state, and detectability. Habitability is not a property of a planet alone. It is a relationship between planet and star. The correlation between stellar metallicity, the abundance of elements heavier than hydrogen and helium in the star's composition, and the presence of giant planets was one of the earliest and most robust results of radial velocity surveys. Stars with higher heavy element abundances are significantly more likely to host detectable giant planets, a result consistent with core accretion theory, which predicts that more metal-rich stars have more solid material available for building the large rocky or icy cores needed to gravitationally capture a gas envelope. This metallicity correlation is less strong for smaller rocky planets, suggesting that their formation is less sensitive to the initial heavy element budget. Small rocky planets can form around stars with a wide range of compositions, while gas giants preferentially form around metal-rich stars. The earliest stars in the galaxy, those that formed within the first billion years after the Big Bang, were dramatically poorer in heavy elements, having formed before generations of supernovae had enriched the interstellar medium with the products of stellar nucleosynthesis. Whether these ancient, metal-poor stars could host planets, and if so, whether those planets could be rocky or only gaseous, was an open question for some time. Discovery of planets around metal-poor stars has confirmed that planet formation is possible even in low metallicity environments. Though the demographics shift, the relative scarcity of rocky planet formation around the most metal-poor stars is consistent with theory. The presence of planets around white dwarfs, the cooling embers left behind by sun-like stars that have completed their evolution, has been established in recent years and carries stark implications. White dwarf atmospheres are expected to be almost pure hydrogen or helium, with heavier elements sinking out of the atmosphere within geologically short timescales due to the intense surface gravity. And yet many white dwarfs show spectroscopic evidence of heavy elements, silicon, iron, calcium, magnesium, in their atmospheres, elements that must have been accreted recently from external sources, because they would have sunk out of the photosphere in thousands to millions of years. The source of this pollution is thought to be the tidal disruption and accretion of rocky bodies, asteroids, minor planets, or even in some cases larger objects, from planetary systems that survive the host star's red giant phase. In effect, the atmospheric composition of metal-polluted white dwarfs is a record of the composition of their surviving planetary material, providing a way to directly measure the bulk composition of extrasolar rocky bodies that no telescope could otherwise probe. Some white dwarfs show evidence of accreting water-rich material, the presence of oxygen in their atmospheres beyond what can be explained by dry rocky accretion suggests planetesimals or larger bodies with significant volatile content. A few remarkable systems show white dwarfs with direct evidence of orbiting rocky debris disks, rings of tidally disrupted rocky material in close orbits, sometimes with additional evidence of ongoing accretion. And one system, WD 1145+017, shows evidence of a disintegrating minor planet in a close orbit, shedding material that produces variable, complex transit signatures, the direct spectacle of a rocky body being ground apart by tidal forces and accreted onto a dead star. The nearest potentially habitable exoplanet to Earth is Proxima Centauri b, orbiting the nearest star to the Sun at a distance of roughly 4.2 light-years. Proxima Centauri, a red dwarf star far dimmer and smaller than our Sun, hosts at least one confirmed planet, Proxima b, and evidence for additional candidates. Proxima b was discovered in 2016 from radial velocity measurements, with a minimum mass of about 1.2 Earth masses and an orbital period of 11.2 days, placing it within the habitable zone of its host star. Nearby systems matter because distance changes everything. A planet 1,000 light-years away can be statistically important, but a planet 10 light-years away can become a physical target. More photons reach our telescopes. the angular separation from its star is larger. Repeated observations are easier. Future direct imaging missions will focus heavily on nearby stars because the search for atmospheres and biosignatures depends on collecting enough light from extremely faint planets. This is why the solar neighborhood has become a strategic map. Proxima Centauri, Alpha Centauri A and B, Barnard Star, Ross 128, Luton Star, Teegarden Star, LHS 1140, and other nearby red and orange dwarfs are not just names. They are the first places where detailed comparative planetology beyond the solar system may become possible. The nearest stars also remind us how hard interstellar distance remains. 4 light-years sounds close only in astronomy. At the speed of the fastest current spacecraft, reaching Proxima Centauri would take tens of thousands of years. Even a future light sail concept traveling at a significant fraction of the speed of light would face immense engineering problems: acceleration, dust impacts, navigation, communication, power, and the inability to slow down at arrival unless even more difficult technology is developed. So for the foreseeable future, exoplanet exploration is remote sensing. We will not walk on these worlds. We will read their shadows, spectra, reflected light, gravitational effects, and timing variations. This can sound limiting, but it is also extraordinary. From a few photons filtered through an atmosphere dozens of light years away, astronomers can infer molecules, clouds, temperatures, and perhaps someday life-related chemistry. The first exploration of exoplanets will not be by spacecraft landing on them. It will be by telescopes learning to understand light with almost impossible care. The discovery of a potentially habitable planet orbiting the very nearest star to our solar system was received with enormous excitement, and it has driven significant scientific attention since. The caveats, however, are significant. We don't know Proxima B's radius. Without a transit detection, we know only its minimum mass, and the actual mass could be much larger if the orbit is tilted significantly relative to our line of sight. We don't know whether it has an atmosphere or, if so, what that atmosphere is composed of. And the habitability question is complicated by Proxima Centauri's intense flare activity. Proxima is one of the most active red dwarfs known, producing regular X-ray and UV flares that could present serious challenges to atmospheric retention and surface habitability. The Breakthrough Starshot Initiative, announced in 2016 by a group of scientists and entrepreneurs, including Stephen Hawking and Yuri Milner, proposed sending a fleet of gram-scale, laser-propelled light-sail spacecraft to Proxima Centauri at a significant fraction of the speed of light, perhaps 20%, with a transit time of about 20 years. Potentially reaching the system within the lifetimes of people alive today. Such spacecraft would carry miniaturized cameras and instruments, producing the first close-up images of another stellar system and potentially Proxima b itself. The engineering challenges are formidable. The laser array required to accelerate the spacecraft would need to produce an output power comparable to a small country's electrical generation. The spacecraft would need to survive bombardment by interstellar dust at 20% of light speed. Communication over 4 light-years with a light sail would need transmitters of extraordinary efficiency, and the entire system would fly past the target in minutes with no ability to decelerate or orbit. Whether this concept will ever be practically realized remains deeply uncertain, but the proposal has focused attention on the interstellar travel problem in a more concrete, technically grounded way than most previous discussions. Alpha Centauri, the binary star system of which Proxima Centauri is an outlying member, has itself been the subject of exoplanet searches. An earlier claimed detection of a planet around Alpha Centauri b was subsequently found to be a statistical artifact. More recent direct imaging attempts and radial velocity searches continue. The Ptolemy spacecraft concept, a dedicated nanosatellite mission designed specifically to search for transiting planets in the Alpha Centauri system from space, represents one of several proposed targeted missions to our nearest stellar neighbors. Ross 128b, orbiting a red dwarf about 11 light-years away, is another nearby temperate rocky planet candidate, of interest partly because Ross 128 is one of the quieter, less flare-active red dwarfs in the solar neighborhood, potentially offering a more stable environment for atmospheric retention than many active M-dwarf systems. It is the kind of nearby target future extremely large telescopes may try to characterize, though detecting a clear atmospheric composition, let alone biosignature gases, would remain technically difficult. LTT 1445AB is a rocky planet orbiting one star of a triple star system only about 22 light-years from Earth. It is one of the few small rocky exoplanets close enough for Webb to attempt thermal emission and atmospheric constraints. Current analyses suggest that it does not require a thick carbon dioxide atmosphere to explain the data, and a bare rock model remains plausible, but thinner atmospheres are not fully ruled out. That is scientifically useful even without a dramatic detection, because a non-detection can still constrain what rocky planets around small stars can retain. Among the most scientifically important nearby systems discovered in recent years is the Teegarden star system, only about 12 light-years away. Teegarden star is a faint red dwarf hosting at least two roughly Earth-mass planets, Teegarden B and C, both at orbital distances placing them near the habitable zone. The system is small enough and nearby enough that it features prominently in future characterization plans, and it represents one of the nearest plausible habitats for life outside our solar system. The statistical results from Kepler, K2, TESS, and ground-based surveys have now produced a fairly coherent picture of exoplanet demographics, the distribution of planet sizes, orbital periods, and host star types across the galaxy. That is one of the most scientifically rich datasets produced by any astronomical mission. The key results can be summarized as follows. Small planets, sub-Neptunes and super-Earths, are the most abundant type, present around roughly 30 to 50% of Sun-like stars at orbital periods of a few hundred days or less. True Earth analogs, Earth-sized planets at Earth-like orbital distances from Sun-like stars, are harder to constrain, but estimates from various statistical analyses suggest they may be present around roughly 10 to 50% of Sun-like stars. Given that there are roughly 200 billion stars in the Milky Way, even the most conservative end of that estimate implies tens of billions of potentially Earth-like planets in our galaxy alone. Gas giants, planets similar to Jupiter or Saturn in mass, are present around roughly 10 to 20% of Sun-like stars at various orbital distances, with hot Jupiters at close orbits being the rarest subcategory at roughly 1%, while cool giants at wider orbits are more common. The occurrence rate of giant planets increases strongly with stellar metallicity and appears to be lower around smaller, cooler red dwarf stars, consistent with the metallicity dependence of core accretion. Multi-planet systems are extremely common. Among stars with one detected transiting planet, roughly 40 to 50% show evidence of additional planets in the system when the data are examined carefully. This is likely an underestimate, given that only a small fraction of planets in any system are geometrically aligned to transit as seen from Earth. Accounting for geometric selection effects, most planetary systems may host multiple planets, a much higher multiplicity than was appreciated before Kepler. Red dwarf stars, the most common stellar type, comprising roughly 70% of all stars in the galaxy, appear to host on average more than one planet per star within the orbital period range accessible to surveys, with higher occurrence rates for small planets around these small stars than around larger, more Sun-like stars. This combination, Small planets preferentially forming around the most common type of star means that the total number of small planets in the galaxy is dominated by planets orbiting red dwarfs, not by planets orbiting sun-like stars like ours. What does all of this mean for the search for life? The sheer numbers are staggering. If even 1% of Earth-like planets orbiting in the habitable zones of their host stars develop life that produces detectable atmospheric biosignatures, there are still potentially tens of millions of biospheres to find in the Milky Way. The distances involved, most such planets being hundreds to thousands of light years away, make direct investigation nearly impossible with any technology foreseeable in the next century. But statistical searches for atmospheric biosignatures across large samples, combined with targeted searches of the nearest systems, represent realistic near-term science goals. The Fermi paradox, the question of why, given the apparent abundance of potentially habitable worlds, we see no evidence of technologically advanced civilizations broadcasting into space, remains as unresolved as ever. But the exoplanet census has at least confirmed that the first term in the Drake equation, the frequency of potentially habitable planets, is enormous. Whatever explanation for the Fermi paradox proves correct, it is not that habitable planets are rare. They are common. Whether life itself is common, whether intelligence is common, whether detectable technology is common, these remain open questions. There is also a psychological danger in the exoplanet catalog. After thousands of discoveries, the word planet can start to feel ordinary again. That would be a mistake. Every detection is indirect in some way. A tiny wobble in a star, a fractional dip in brightness, a slight timing change, a temporary brightening by gravitational lensing, a faint infrared point near a young star. From signals this small, astronomers reconstruct worlds, masses, radii, densities, orbits, temperatures, atmospheres, and sometimes weather. The catalog looks like a list, but behind every entry is an active measurement at the edge of what light can tell us. This is why exoplanet science is not just the discovery of objects. It is the discovery of methods capable of finding worlds that cannot be seen directly. The achievement is double. The planets are real, and the measurements are delicate enough to reveal them. The future of exoplanet science will unfold over the next several decades through a combination of increasingly powerful space telescopes, ground-based giants, and possibly dedicated space missions aimed specifically at atmospheric characterization. The Nancy Grace Roman Space Telescope, NASA's next large space telescope slated for launch in 2026, will carry a coronagraph, an instrument designed to block starlight and enable direct imaging of planets in reflected light, as a technology demonstration, providing the first space-based coronagraphic observations of exoplanets and paving the way for the dedicated mission that follows. It will also conduct a gravitational microlensing survey that will, for the first time, characterize the occurrence rate of cold, outer solar system-like planets at wide orbital separations, the part of the exoplanet period mass parameter space that transit and radial velocity surveys struggle most to reach. The European Space Agency's Plato mission, planned for launch around the end of 2026 or early 2027, will survey nearby bright stars for transiting planets, with a particular focus on Earth-sized planets at Earth-like orbital periods around Sun-like stars, exactly the configuration most likely to mirror our own situation, and the configuration hardest for previous missions to detect definitively. Plato's longer baseline and high photometric precision aim to provide the first reliable statistical characterization of true Earth analogs. The Habitable Worlds Observatory, a concept developed through the most recent U.S. Decadal Survey in Astronomy, is the proposed flagship NASA space telescope specifically designed to directly image Earth-like planets around nearby Sun-like stars in reflected light and obtain their spectra, searching for biosignature gases. It would need to suppress the light of the host star by a factor of 10 billion or more to reveal the faint reflected light of an Earth-like planet, requiring coronagraph technology significantly more advanced than anything yet built. The mission is in the early stages of design, with launch potentially in the late 2030s to 2040s if funding and development proceed on schedule. The extremely large telescope, now under construction on Cerro Armazones in the Atacama Desert of Chile, with its 39-meter primary mirror, will have the angular resolution and light-collecting power to directly image some rocky planets in the habitable zones of the nearest red dwarf stars and to attempt spectroscopic characterization of their atmospheres. Its adaptive optics systems, correcting for atmospheric turbulence in real time, will provide image quality approaching the theoretical diffraction limit of a 40-meter telescope, opening the door to the kind of direct planet characterization previously reserved for space-based coronagraphs. The next generation of exoplanet science is not only about finding more planets. It is about moving from discovery to comparison, and from comparison to context. Roman and Plato will change the catalog in different ways. Roman's microlensing survey is expected to look toward the dense star fields of the galactic bulge, where many background stars create many opportunities for gravitational lensing. It should be sensitive to planets at wider separations than typical transit surveys, including cold planets that orbit far from their stars and planets with masses down toward Mars in favorable cases. It may also detect free-floating planets through short microlensing events. This matters because our current catalog is dominated by close-in planets, not because close-in planets are the whole galaxy, but because they are easier to detect repeatedly. Plato, by contrast, is designed to observe bright stars over long periods, with special attention to small planets around Sun-like stars. Its advantage is not just planet detection, but stellar characterization. By measuring oscillations in host stars, astroseismology, Plato can determine stellar ages and sizes more accurately. That improves planet radii and helps place planets in time. A rocky planet's meaning changes if it is 1 billion years old or 8 billion years old. Habitability is not only about location, it is also about duration. The extremely large telescope will approach the problem from the ground, using its enormous mirror and adaptive optics to separate faint planetary light from nearby stars in selected systems. Ground-based telescopes face Earth's atmosphere, but they also can be huge in a way space telescopes rarely are. A 39-meter mirror collects an enormous amount of light, and with advanced instruments it may study atmospheres of some nearby rocky planets around small stars. The Habitable Worlds Observatory, if built, would represent the more distant ambition, a space telescope designed from the beginning to search for life-related atmospheric signatures on Earth-sized planets around nearby stars. It is not a guaranteed mission with a simple launch date. It is a concept moving through design and planning, shaped by the priorities of the astronomical community. But its goal defines the direction of the field. The next great step is not only discovering planets. It is separating a pale, rocky world from the glare of its star and asking what its atmosphere means. The first era asked, do planets exist around other stars? The answer is yes. The second era asked, how common are they? The answer is that they are extremely common. The current era asks, what are they like? That requires atmospheres, densities, orbital architectures, stellar activity histories, and planetary ages. The future era will ask an even harder question. Which of these worlds, if any, show signs of biology? The Habitable Worlds Observatory concept is important because it is designed around that question. The goal is not merely to find another planet roughly the size of Earth. The goal is to directly image Earth-like planets around nearby Sun-like stars, separate their faint reflected light from the overwhelming glare of the star, and spread that light into spectra where oxygen, ozone, water vapor, methane, carbon dioxide, and other molecules might be identified. This is extraordinarily difficult. It requires suppressing starlight by factors of billions to tens of billions, holding optical systems stable at extreme precision, and interpreting faint signals where false positives and false negatives are both possible. Even a strong biosignature candidate would not end the scientific process. It would begin a new one. Astronomers would need repeated observations, independent analysis, stellar context, climate modeling, geochemical modeling, and a careful search for abiotic explanations. The first plausible biosignature beyond Earth may be ambiguous. It may not be a single dramatic announcement, but a long accumulation of evidence. That may be frustrating, but it is how a discovery that important should happen. The question of life beyond Earth deserves excitement. It also deserves discipline. These missions and facilities together define the scientific program of the next generation of exoplanet research. Within the lifetimes of people alive today, it is conceivable that we will have obtained spectra of at least some rocky habitable zone exoplanet atmospheres, and perhaps eventually enough to begin statistical comparisons across different types of planetary systems. The first credible, if still uncertain, assessment of biosignature gases on a specific nearby world may become one of the central scientific goals of the next generation of observatories. Whether those assessments lead to a detection of life, or to the conclusion that life detectable this way appears absent from the nearest systems, will be one of the most significant scientific results in human history either way. There is a quiet reversal in all of this. For thousands of years, humans looked at the stars and imagined worlds because we had no evidence. Now we have evidence, and the imagination has to become more careful. We can no longer picture other planets only as second Earths, second Jupiters, or fictional landscapes. The real catalog is stranger. Planets with years shorter than a week, planets evaporating into space, planets orbiting two stars, planets circling stellar corpses, planets packed into resonant chains, planets that may be half rock and half atmosphere, planets with no star at all. The search has made the universe larger, but also more specific. Other worlds are no longer an abstract possibility. They have names, radii, masses, periods, host stars, spectra, densities, equilibrium temperatures, and uncertainties. They can be plotted. They can be compared. They can be wrong in our models and force the models to change. And somewhere in that catalog, perhaps not yet identified, there may be a world whose atmosphere is being altered by life. Not necessarily intelligent life. Not necessarily forests or animals or oceans like Earth's. Perhaps only microbes changing chemistry under a sky we would not find breathable. Perhaps something stranger, using energy and chemistry in a way Earth's biology never discovered. The first life we find beyond Earth, if we find it, may not look like a mirror. It may look like a puzzle. That is why exoplanets remain one of the most powerful subjects in modern astronomy. They connect physics, chemistry, geology, climate, and biology. They ask how planets form, how atmospheres survive, how stars shape their worlds, and whether life is a planetary process that happens often when conditions allow, or a rare outcome of Earth's particular history. Exoplanets also changed the meaning of Earth. Before the exoplanet era, Earth could be compared only to the other worlds of the solar system. Venus showed the danger of runaway greenhouse conditions. Mars showed atmospheric loss and cold desert evolution. The outer moons showed ice, oceans, tidal heating, and chemistry far from sunlight. But all of these worlds formed around the same star, from the same disk, inside the same broad chemical environment. Exoplanets widen the comparison. Earth can now be placed among rocky worlds around red dwarfs, compact super-Earth systems, old planets around ancient stars, planets around metal-poor stars, planets in binary systems, and worlds that formed in environments unlike the Sun's birth cloud. This does not make Earth less special in the sense that life is known here. It makes Earth more scientifically defined. We can ask which of Earth's properties are common and which are rare. Is it rare to have a large moon? Rare to have long-term plate tectonics? Rare to have the right amount of water? Rare to avoid destructive migration by giant planets? Rare to keep a stable climate for billions of years? Rare to develop oxygenic photosynthesis? Rare to produce technology? Exoplanets do not answer all these questions yet, but they finally make the questions empirical. The deepest impact of exoplanet science may therefore be delayed. The first decades gave us abundance and diversity. The next decades may tell us where Earth sits in that diversity. Not whether it is emotionally special. It is, because it is home, but whether its physical path is common or unusual. It is worth taking a moment simply to sit with the scale of what the past 3 decades have revealed. Before 1992, we knew of 9 planets, 8 around our Sun, and 1 discovered circling a pulsar. We had no confirmed knowledge of whether any other star in the galaxy hosted any planet at all. The question that civilizations had contemplated for thousands of years was simply unanswered, possibly unanswerable. Today, we know of more than 6,000 confirmed planets around other stars, with thousands more candidates. We have measured the atmospheric compositions of dozens of them. We have identified planets with water vapor, carbon dioxide, hydrogen, helium, and in one controversial case, the possible presence of sulfur-bearing molecules such as dimethyl sulfide has been debated, without amounting to a detection of life. We know that rocky planets are common. We know that potentially habitable rocky planets are common. We know that multi-planet systems are the norm rather than the exception. We know that our own solar system, with its large gap between rocky inner planets and giant outer planets, is architecturally unusual by the standards of the galaxy. We know that the nearest star to our Sun, for light years away, appears to host at least 1 planet in the habitable zone. We know that small, cool red dwarf stars, the most common stars in the galaxy, routinely host rocky planets in their habitable zones. We know that gas giants can exist in extraordinary proximity to their stars, so close they are being actively eroded, shedding mass at each orbit, spiraling toward eventual infall. We know that rogue planets, untethered to any star, may be as common as stars themselves. We know, in short, that worlds are everywhere. The galaxy is full of them. They come in every configuration, every composition, every orbit that the laws of physics will allow, and quite a few that the prevailing theories didn't expect. Hot Jupiters, ocean worlds, diamond-rich mantle planets, lava worlds, super-Earths, mini-Neptunes, puffy giants barely denser than Saturn, dense iron worlds, tidally locked rocky planets with one side in permanent noon and the other in permanent midnight. And among all of these, somewhere, on some rocky world orbiting in the temperate zone of some ordinary star, the right combination of chemistry, energy, and time might already have produced something that looks upward from its surface and wonders what else is out there. We're wondering the same thing. From our own rocky world, around our own ordinary star, after 30 years of an extraordinary search that has only just begun. The answer, in all its strange and surprising diversity, is turning out to be more extraordinary than we imagined. For now, the catalog keeps growing. More worlds are added. Some are confirmed, some are rejected, some are revised, and some become targets for the next telescope. The search is no longer a philosophical hope. It is a continuing measurement of the galaxy. One more important fact is that exoplanet science is still young enough that the catalog is uneven. Some stars have been watched for decades with radial velocity instruments. Others have barely been monitored. Some parts of the sky were in Kepler's original field and received years of continuous attention. Other regions were observed by tests for only weeks. Bright nearby stars are easier to follow up than faint distant stars. Planets around quiet stars are easier to detect than planets around active stars whose spots and flares create noise. A small planet around a small star may be easier to detect than a larger planet around a larger star, simply because the relative signal is cleaner. This means the known population is not identical to the real population. It is the real population filtered through instruments, observing strategies, mission lifetimes, detection thresholds, and human priorities. The true galaxy contains more long-period planets than the confirmed catalog currently shows, more cold planets, more small planets in wide orbits, more planets around faint stars, and probably many more free-floating worlds. Every new method fills in a different missing region. Radial velocity extends with time, gradually revealing planets in longer orbits. Transit surveys expand with more stars and better precision. Microlensing surveys probe the cold outer systems. Direct imaging improves contrast and moves towards smaller, older planets. Astrometry adds true masses and wider orbits. Atmospheric spectroscopy moves beyond detection toward physical understanding. The exoplanet catalog is therefore not a finished map. It is a coastline emerging from fog. The first outlines are clear enough to show that the territory is vast, but the interior still contains unknown continents. This is why each confirmed planet still matters. A single new world can occupy a rare part of parameter space. It can test a formation model, challenge an atmospheric theory, reveal a new kind of system, or provide a nearby target for future telescopes. The number is now in the thousands, but the science has not become routine. The variety keeps preventing routine. The most interesting discoveries may still be ahead. The first confidently characterized Earth-sized atmosphere around a temperate rocky planet. The first direct image of a true Earth analog. The first convincing biosignature candidate. The first detailed weather map of a small exoplanet. The first census of cold planets from Roman. The first robust comparison between habitable zone planets around red dwarfs and those around sun-like stars. The next chapter will not simply ask whether planets exist. It will ask what planets become. Even the failures in exoplanet science are useful. A claimed planet that disappears after better data teaches astronomers about noise, stellar activity, and the limits of detection. A planet candidate that turns out to be an eclipsing binary improves validation methods. A biosignature claim that weakens under independent analysis teaches caution about atmospheric retrievals and the danger of overinterpreting faint spectra. A model that fails to predict a new class of planets forces theory to become broader. This has happened repeatedly. Hot Jupiter's forced migration into the center of planet formation theory. Super-Earths force scientists to explain why the most common close-in planets have no solar system analog. The radius gap turned atmospheric escape into a population-level process. TRAPPIST-1 made red dwarf habitability a central question. Jumbo-like candidates forced discussion about whether planetary mass objects can form in pairs without stars. Each surprise expands the theory. So the exoplanet catalog is not just a list of successes. It is a record of corrections. Astronomy learns by being wrong in public, then becoming more precise. That is part of why this field is so alive. The data still have enough power to embarrass old assumptions. The universe did not build planets to match the first theory humans wrote down. It built them according to physics, and physics allows more variety than expectation did. There is also a quieter consequence of the exoplanet revolution. It changes how we imagine the night sky. The stars no longer appear only as distant suns. Each one becomes a possible system. A faint red dwarf may host compact rocky planets. A bright F-type star may have giant planets in wide orbits. A white dwarf may carry the remains of disrupted asteroids in its atmosphere. A binary star may have planets moving around both suns. Some stars may have lost planets to interstellar space. Some may be surrounded by young disks where planets are still forming. Some may have stable systems billions of years older than our own. The sky therefore becomes populated in a new way. Not visibly, the planets remain hidden, but conceptually. The dark spaces between stars are not empty of worlds. Some worlds are in tight, hot orbits, some in cold, distant orbits, some drifting alone, some locked in resonant chains, some wrapped in hydrogen, some stripped to bare rock, some drowned in deep oceans, some glowing with internal heat. This does not mean that every star has a habitable planet. It does mean that planet formation is a normal outcome of star formation. The same disks that build stars often build worlds. The galaxy is not only a stellar system. It is a planetary system multiplied hundreds of billions of times. And that makes Earth's situation more precise. Earth is no longer the only known planet in the universe outside imagination. It is one planet in a measured population, but still the only planet known to be alive. That combination is powerful. Abundance surrounds uniqueness. We know worlds are common. We do not yet know whether biospheres are common. We know chemistry can build planets everywhere. We do not yet know how often chemistry becomes biology. This is why exoplanets hold attention so strongly. They give science both certainty and mystery. Certainty that planets are everywhere. Mystery about what those planets become. The question is no longer whether other worlds exist. The question is whether any of them have oceans under alien skies, whether driven by unfamiliar suns, continents no eye has seen, clouds made of water or rock or metal, or atmospheres quietly altered by living chemistry. The question is whether life is a local accident or a galactic habit. And for the first time in history, that question is not only philosophical. It is observational. A telescope can test it. Not fully yet, not easily, and not without ambiguity. But the path is real. Find the planet, measure its size, measure its mass, determine its orbit, study its star, search for an atmosphere, identify molecules, test false positives, compare models, and repeat. Step by step, a point of light becomes a world with constraints. Step by step, the galaxy becomes less anonymous. There is also an important emotional discipline in this subject. Exoplanets invite exaggeration because every discovery sounds like a doorway. A rocky planet becomes another Earth. A temperate orbit becomes a living world. A molecule becomes a hint of biology. But the real story is stronger when it remains exact. A planet can be fascinating without being habitable. A system can be important without resembling the solar system. A spectrum can be meaningful without proving life. Science does not reduce wonder by adding caution. It protects wonder from collapsing under claims that the evidence cannot support. That is the tone this subject deserves, not cynicism and not hype. The correct response to thousands of confirmed worlds is not to pretend we have found life and not to dismiss the possibility. It is to recognize that the galaxy has supplied the first half of the answer. Worlds are common. The second half, whether living worlds are common, remains open. The next confirmed planet may be ordinary. It may be another small world close to a red dwarf, another warm sub-Neptune, another giant planet in a short orbit. But even ordinary discoveries matter now because ordinary is exactly what the catalog is trying to define. Only after thousands of worlds can astronomy begin to say what typical means. And only after typical is understood can Earth be placed honestly against the background of the galaxy. That is why the catalog itself is a scientific instrument. It is not only a record of named objects. It is the statistical mirror in which planetary science sees its own assumptions. Every new planet slightly changes the distribution of what is possible, what is common, what is rare, and what still has not been found. And because the catalog is still incomplete, the next surprise is not a possibility at the edge of the field. It is almost expected. The history of exoplanets has been a history of the universe answering carefully designed questions with answers broader than the questions themselves. For a subject this young, that is the correct ending, not closure, but a wider map and better questions. The galaxy has given us abundance first, meaning will take longer. And the search continues, one careful signal at a time. And we leave it there, not with one other Earth, not yet with life, but with something almost as important, the knowledge that planets are everywhere, and that the story of worlds has barely begun. Good night.